Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. Assalamu alaikum, everyone. So today we will solve recitation problem for chapter 29. So we already start solving a few problems in class. We solved, I think, 3 or 4 problems already. Let's go through them. So we solved this problem, if you remember correctly, okay, how to find this resistance R. So we calculated the force between the 2 parallel wires, and then we got the resistance R. Okay, great. Here we already calculated this using, of course, Ampere's law. So we calculated this current I3, and we show that it's coming out, right? Next, we solve this as well, which is a torque acting on the coil due to the loop. So we solve this, and the solution is given. We discussed this in class already. Now we start solving this problem, but let's go through it in detail, and then inshallah we will solve this one. Okay, so what do we have here? We have a long straight cylindrical conductor of radius R, which has 12 millimeters. Okay. It carries a current I uniformly distributed over its cross section. I did not give you I, by the way. Okay. So first mission is to find I, but we will see. If the magnitude of the magnetic field produced at a distance R outside at a distance R 24 millimeters is 0.1 millitesla, then what is the magnitude of the magnetic field at a distance R, which is 8 or 6 millimeters? Okay, great. So let's have a cross-sectional view. This is my cylindrical wire, magnified, of course. This radius R, capital R, I gave it to you, is 12 millimeters. Let's assume that the current is pointing towards you, okay? So it's coming towards out. So let me just put like this. So the current I is coming out of this cylindrical wire, okay? I did not give you I, okay? So I is a total current coming out of this cylindrical wire, I. It's in amp, of course. So I did not give it to you, but no problem, we will find it. And I is uniformly distributed over the cross-sectional area. Of course, you see, this is very important. So the current density is uniform, constant over the whole cross-sectional area. Great. Now, if the magnitude of the magnetic field produced by this long, straight cylindrical conductor carrying a current I at a distance R, so let me call it distance R here. Let me call it R1. So this distance from the center, I call it R1, and R1 is equal to 24 millimeters. So B1 here, which is basically this is 0.1. B1, which is the magnetic field here, is just equal to 0.1 10 to the power minus 3 Tesla. Okay. Okay, so you know that B outside my wire, when R is bigger than capital R, this is very simple. It's just mu naught pi divided by 2 pi R. That means, of course, my B1 here is just mu naught I divided by 2 pi R1. Okay. So I know actually what is I. Of course, I will be 2 pi R1 multiplied by B1 divided by mu naught. Okay. Great. Now, second, I'm now asking you what's the magnitude of the magnetic field at a distance R here inside. So here, let me call it R2. So this distance here, I call it R2. So R2 is equal to 6 millimeters. So now the question is, what is B2? When R2, of course, R2 is smaller than capital R. So inside, what is B2? The magnetic field inside my cylindrical wire. course, magnetic field inside we have demonstrated in class, and it's in your formula sheet, is equal to mu naught multiplied by I, right? Divided by 2 pi r square, r being the radius, multiplied by r. So here it will be r2. Okay? This formula we demonstrated it using, of course, the uniform current density and using, of course, the Ampere's law. Okay, inside the magnetic field inside, this is outside, but B inside, when R is smaller than capital R, is just mu naught current divided by 2 pi radius square multiplied by the distance R. Okay, R is how far I am from the center. So you just use that here. So this is B2 that I want. Well, B2 will be just mu naught divided by 2 pi capital R square multiplied by I, R2, now multiplied by I. Now I will just take this formula here and just plug it in. So I'll have 2 pi R1 divided by mu naught P1. So 2 pi will simplify, of course. Mu naught will simplify. And I have that B2 will be R2 R1 divided by radius square multiplied by B1. Okay, this is my B2. If you use the numbers that I gave you here, you will see that actually B2 is just equal to B1. Because this R2, I know it, it's 6, R1 is 24, so R square is 12 square. So this ratio here will be just 1. This ratio here is just 1. Okay, for the numbers I gave you. Okay, that's why B2 is equal to B1. But of course, if this I did not have these numbers R1, R2, R3, I will have a different number. So of course it will be different. But here the answer is just this. Okay, B2 is equal to B1 and it's equal to 0.1 millitesla. Okay, great. Let's go to the next problem. So the question is very simple. For what value of radius R of the loop shown in the figure 9, you see the loop, is the magnitude of the net magnetic field at the center of the loop here, so B center, at the center is equal to 5 10 to the power minus 5 Tesla. So what is the radius R of my full circle? Okay, here's the loop carries current, of course. So I have a current I, which is moving forward here, and I is equal to 1.2. I is equal to 1.22 amp. Okay, great. So what do we see here? Well, my system can be decomposed into an infinitely long wire, as that you can see here. And I can calculate what is the magnetic field created by this infinitely long wire at the center here, which is at a distance R. A perpendicular distance. So the magnetic field B wire created by this infinitely long wire at this point, which is the center, is just mu naught I divided by 2 pi multiplied by the perpendicular distance, which is R here. Okay, great. Now, the second part of my system is the loop. Now, what is the magnetic field created by the loop? Well, easy. It's mu naught I phi divided by 4 pi radius. Now, since this phi here should be in radian again, okay, this is a magnetic field created by an arced wire of angle phi, okay, and radius r. So you remember that we said that if I have an arc, okay, let's say this is the center C, and this is the radius r, and I have current which is carried here, and this angle is theta or phi, let me call it phi. The magnetic field created by this arced wire, of course, at the center here is just mu naught multiplied by the current divided by 4 pi radius multiplied by phi. Okay. So here, of course, phi is equal to 2 pi because I am covering a full circle. I just get B loop is mu naught multiplied by current multiplied by 2 pi divided by 4 pi, which just gives you 2R. And we already demonstrated this in class. Great. Now here, let's look at the direction of the magnetic field. What is the direction of the magnetic field created by this infinitely long wire at the center here? You use the right-hand rule. Your thumb with the current, your fingers will be pointing inward. Okay? So of course, this direction is inward. So inside the page. Okay. What about for the loop? What the direction of circulation of the current in my loop? The current is going in this direction. Okay? So the current is doing this, then circulating in this loop, of course, clockwise. Okay. So that means if I use my right-hand rule also, of course, I have the direction of my magnetic field at the center, which is also inward. So same direction. So my net magnetic field, B net, will be the sum of two magnetic fields pointing up inward. Okay, so it will be a sum plus. If one was pointing inward, one is pointing downward, so you will have a minus. Okay, but here the net magnetic field will be B wire plus B loop. If I calculate it, I can put in common factor mu naught I divided by 2R. Okay, now here I will have 1, and here I will have 1 over pi. You do the calculation. I know everything. I know mu naught. What is mu naught? 4 pi 10 to the power minus 7 Tesla meters divided by amp. Okay. It's in your formula sheet. This is the permeability constant. Okay. Great. Now, what is my I? I know I call it capital I here. So it's 1.22. I know R. What is R? R is what I want, by the way. Okay. So I don't know R. But I know that this B net here is 5, 10 to the power minus 5. So let's get R. Of course, R will be just mu naught I divided by 2B net, 1 plus 1 divided by 5. You put everything, then you get your R. Okay, you know everything, so you get your R, and R will give you just 2.02 10 to the power minus 2 meters. Okay, 2.02 centimeters. Is it clear? So you know how to calculate the magnitude of the magnetic field, but also the direction and how you can calculate the net magnetic field. Okay. Of course, net magnetic field, you have to be careful because now you need to know both of the magnetic fields are pointing in the same direction. Of course, you add them because in opposite direction, you look at the algebraic sum. Yes, right? Pointing outward is positive, pointing inward will be negative. Okay? And you will see which one will dominate. I will show you an example just in a second about it. Okay, great. Now let's solve this problem here. Let's read it very carefully. Again, a long, straight cylindrical wire, and I give you the radius, 12 centimeters. And I give you the current, because the current is uniformly distributed over the cross-sectional area. Okay? Otherwise, I have to give you the current density, which will be radially dependent. If the current density is uniformly distributed, so that's easy. You know that the current density does not depend on the radius. It's a constant. And I already discussed that in class, and you know that very well. So the current here is equal to 3 amp, and it's uniformly distributed over the cross-sectional area. Let me draw again. This is my cylindrical wire. Of course, this is a top view or a cross-sectional view. The current is pointing towards you. This is the center. Let's say that it's coming towards you, okay? The current is coming out and it's uniformly distributed. So I is equal to 3 amp and it's uniformly distributed across this cross-sectional area. Okay, good. Now, the question is at what radial distance from the center, of course, inside the wire is the magnetic field produced by this current equal to half of its largest value. Right? Great. So what you need to know here is how is the magnetic field inside and outside? We said that magnetic field outside, when R is bigger than the radius, is just mu naught I divided by 2 pi R, R being the perpendicular distance. When I'm at this distance R from the center, I can get what the magnetic field here by knowing this perpendicular distance between the center and the point I'm looking at. Okay? And you see that here, of course, the magnetic field is inversely proportional to the distance. But inside, this is outside, as we discussed already. B inside, when R now is smaller than capital R, B inside is mu naught I being the current, by the way. So here I can call it capital I if you want. The total current, okay? Divided by 2 pi capital R square multiplied by R. And this is inside. Okay, these are the magnitude of the magnetic field created by this long straight cylindrical wire of radius R outside the wire and inside the wire. Outside the wire is proportional to 1 over R, and inside the wire is proportional to R. So we plotted this, by the way, in class. So this is B. This is a radial distance, and this is the radius of the wire. When it's 0, the B is 0. So as long as I am here, of course, I am inside. I have a linear dependence between the magnetic field and the radius. Okay. Now, once I reach here, now I am now outside. I will have 1 over R. Okay. This behaves as 1 over R, and this behaves proportional to R. And of course, the maximum value, you see it here. The maximum value is just B at the surface of my cylindrical wire. And B at the surface of my cylindrical wire, that's easy. That's just mu naught I divided by 2 pi R. Okay, this is a maximum value. Okay, great. Now, if I ask you at what radial distance inside the wire is a magnetic field created by this current half of its maximum value, you know that I have to divide the maximum value by 2. That means I have to divide the R by 2. Okay, because you see here, this is inside, right? Okay, when when R is equal to capital R, which is at the surface of my wire, I can just put it here and I find that it's mu naught I divided by 2 pi R. This is a maximum value. Okay, this value here is max. This is a maximum value. Okay, now inside, I need B max divided by 2. That means I will reach that when R is equal to R, the half of the radius. Okay, when R is half of the radius. So when R is half of the radius, I will reach that. So that's why here you don't need to calculate. You know that, of course, it will be 6 because the radius is 12 centimeters. Does it make sense? Okay, because here this is my max. I need half of it. Of course, half of it will be half of this. So this is R over 2. Okay. If I ask you at what radial distance inside the wire the magnetic field produced is equal to 1/4. So of course I will divide the B max here by 1/4. Okay, so here, so this is 1/4 B max. And of course this will correspond to 1/4 of the radius. Okay, you get my point? Now, this is inside. In the exam, I can ask you inside, of course, but I can ask you outside as well. Now, the question is very simple. At what radial distance, same question, but now outside the wire? I just replace this inside by outside. Okay? Is the magnetic field produced by the current equal to half of its largest distance? Well, so all what you need to do is to apply the formula. So of course, B outside is just mu naught I divided by 2 pi R. Now this should be equal to half of the max value. What's the max value? The max half of the max value, which is just mu naught I divided by 2 pi R. So let's simplify. Mu naught I, 2 pi, and you end up with R is just equal to 2R. So basically this half will correspond to 2 times R here. Okay. So when I look here, outside, this is 2R. Okay. So for each magnetic field, I have a value inside and a value outside that correspond to it. Okay. For each magnetic field created by the wire. Great. So here, if I said outside, of course, R will be 2R, 2 times the radius. Does it make sense? Great. Let's go to the next question. So I delete this. So the next question is very important. I have a solenoid and I give you the length of the solenoid. So the length of the solenoid, let me call it capital L. L is equal to 1.3 meters. And I give you the diameter of the solenoid. Okay? This is the diameter of the solenoid. So you know that the radius of the solenoid is just 1.3 centimeters. Okay? So it carries a current of 18 amps. And the magnetic field inside the solenoid is 23 millitesla. So I know I, 18 amp. And of course, I gave you the magnetic field inside the solenoid, which is 23 10 to the power minus 3 Tesla. And the question is very simple. Find the length of the wire forming the solenoid. So how can we get the length of the wire forming the solenoid? Let's draw the solenoid very quickly. Okay, so this is my solenoid, etc., etc. It can be more tight, but just for illustration. Okay, this is the length of the solenoid, L, 1.3 meters. And this is the diameter of the solenoid, D, of course, which is 2R, 2 times the radius of the solenoid. Anyway, so the current which is going through my solenoid, let's say that it's going in this direction. Okay, this current is equal to 8 amp. And the magnetic field inside my solenoid is 23 millitesla. Okay, so, and the question is find the length of the wire, not the solenoid, okay, because we already know the length of the solenoid. We want the length of the wire, L wire. Okay, great. We know that the magnitude of the magnetic field created by the solenoid is constant inside the solenoid. And you remember that a solenoid creates inside it a uniform magnetic field. And that uniform magnetic field, we calculated it by Ampere's law. It's equal to mu naught N multiplied by the current I. Mu naught, you know it. N is the number of turn per unit length. Okay, you remember N is number of turns. We already talked about this in class. Per unit length. Per unit length. In other words, N is capital N, which is the total number of turns divided by the total length of the solenoid. Okay? So this is N, capital N divided by L. Okay, N is capital N divided by L. So capital N is the total number of turns, and L is the length of the solenoid. Here, of course, L is 1.3. Okay, great. And then I multiply by I. So here, this magnetic field is just 23, 10 to the power minus 3 Tesla. So I can know what's the number of turns because I know everything here. I know mu naught, it's a constant. I know I, it's 18 amps. I know L. So the number of turns, N, let's write it down, V is equal to B, magnetic field inside the solenoid, multiplied by the length of the solenoid, divided by mu naught, multiplied by the current. You put all the numbers, it's of course 23 10 to the power minus 3, multiplied by the length, 1.3 meters. Of course, you put everything in SI units, divided by 4 pi mu naught 10 to the power minus 7 Tesla meter per amp. Okay, I is of course in amp, 18. So this gives you what? If you calculate, you get 1,322 turns. Okay, this is the number of turns, the total number of turns. Now, knowing the total number of turns can help me get the total length of the wire forming the solenoid. So see here, this is one turn, by the way. Okay, this is one turn. Okay, I start from here, I go all around, I have one turn. So each turn, you can say each turn has a length of 2 pi r, okay? Because each turn is a circle, okay? If r is the radius of the solenoid, each turn has a length of 2 pi r. Okay? So n turn, the total length of the wire is just n turn, n multiplied by the length of each turn. So n times 2 pi r. So this gives me the total number, the total length of the wire. You got my point? Okay. So of course here the wires should be, tightly one after the other, basically. Okay? The length will be larger than this, but this is when it's tight, basically. Okay. Great. So what do I have? I have total number of turns, which is 1,322, and then I multiply by 2 pi r, which is the length of one turn. So 2 pi multiplied by, what is r? 1.3 10 to the power minus 2. And this gives you 108 meters. Okay. So the total length of the wire forming the solenoid is 108 meters. Okay. So we have 108 meters, and we just wrap it around a solenoid, a cylinder which has a length of 1.3 meters. Okay. If you want to remember things, of course, this you know it, it's in your formula sheet. This you should know it, of course. This also you know it. Now remember this, total length of wire is number of turn multiplied by the length of one turn, which is 2 pi r. That's it. Next. So read this problem very carefully and we solve it quickly. So in this figure 3, we have a closed loop, okay, carrying current, and I give you the current. I is 0.2 amp, okay, 200 milliamp. You put everything in SI units, 0.2 amp. Great. The loop consists of 2 radial straight wires and 2 concentric circular arc of radii 2 meters and 4 meters. The angle is pi over 2. So this angle here, theta, is 90 degrees, pi over 2. Okay. The angle should be in radian. Great. If I give it in degree, you put everything in radian. Okay. What are the magnitude and direction in or out of the page of the net magnetic field at the center of the curvature? P. So I want the magnetic field here at P. First, let's decompose my closed loop into 4 parts. Okay. So let me call this part 1. The current is going in this direction. Okay. This is part 1. This is the first arc. Okay. And this second arc, I call it part 2. Okay. So you see the current is going in this direction. The current is going in this direction, as you can see, right? Current is going in this direction, and of course it's going in this direction. Okay. So this is my current I. Okay. Okay. So part 1 is a large arc. Part 2 is a second arc. Okay. The smaller arc, circular arc. Part 3 is this linear part here, and part 4 is this linear part also. Great. So first thing first, what can we say? The net magnetic field at P is equal to magnetic field created by part 1 plus magnetic field created by part 2. Part 1 and part 2 are the 2 arcs, plus the magnetic field created by part 3 plus the magnetic field created by part 4. But the magnetic field created by part 3 is equal to the magnetic field created by part 4 is equal to 0. We discussed this already. Why? Because on these two parts, 3 and 4 that are linear, ds is parallel to r. So that means ds cross r is equal to 0. Okay? So you see here ds is like this and r is like this. Okay? So here as well. So it will be 0. So these two here, I can forget about them. 0, 0. So the net magnetic field will be due to the two arcs. Okay? The two concentric circular arcs. Okay? Great. Now this one here, okay, has a radius r1. The big one has a radius r1. So r1 is equal to 4 meters. And r2 is a small arc. Okay, basically 2 meters. Now, let's look at the direction. Okay? Let's look at the direction B1. What's the direction of B1? What do you think? The direction of the current created by arc 1, which is this arc, the big arc. This is arc 1. So you use the right-hand rule, right? Of course, my thumb will be pointing along the direction of the current. You see that my fingers are pointing out of the page. Okay? So B1 is pointing outward or out of the page. Okay? Let me consider that out of the page is positive, let's say plus. Okay? Now B2, what's the direction of B2? B2 is created by the second arc. You see here, the current is going in which direction? Clockwise. So if I use that, what do I see? Of course, B2 is directed. I use the right-hand rule, my thumb along the current, my fingers are pointing inward. Okay? So B2 is directed inward, inside the page. Okay? So I will take it as negative because out of the page correspond to plus Z. This is plus Z direction. Oh no, plus K hat direction. Inside is minus Z direction, basically negative Z direction, minus K hat direction. Okay. Okay, so if I project my B net here, as I said, is B1 plus B2. If I project along the Z direction, I get that B net is equal to B1, but B1 is positive, plus B1 minus B2. Okay. Great. Okay. So now the plus B1 because it's pointing outward, so the plus is here. Minus because B2 is pointing inward, so the minus is here. Now B1 and B2 here are just magnitude. Now what's the magnitude of B1? Well, magnitude of B1 is mu naught multiplied by the current multiplied by phi divided by 4 pi multiplied by R1, small r1. Or let me put capital R here. Capital. There's the radius. Okay. So I know everything. This is mu naught. This is I know phi. Phi is just pi over 2. You put it in radian. Of course, divided by 4 pi multiplied by the radius R1, which is 4 meters. And B2, I know it also. B2 is equal to what? Mu naught I phi. Now phi is also pi over 2 divided by 4 pi multiplied by R2. Okay. R2 now here is equal to 2 meters. Okay. R2 is 2 meters. Great. So what do you get? This I will get 4.71 10 to the power minus 8 Tesla. And B1 I get something like 2.36 10 to the power minus 8 Tesla. Now let me put it here. I find that B net, when I project, so because here I'm projecting along Z, when I project, I just find it's equal to basically 2.36 minus 4.71, everything 10 to the power minus 8. So this gives me just minus 2.36 10 to the power minus 8 Tesla. So this is the right answer. Now the negative sign is telling you that, of course, it's pointing way inward. into the page. Okay, so this is the right answer. Okay, into the page. Okay, I knew that because I know that this wire here is closer, so it will create a bigger magnetic field at the center. Okay, so inward, I know the magnitude and I know the direction inward or into the page. Okay, now let's go to the next problem. Any question? Okay, if you have a question, don't hesitate to bring them in class. Okay, now figure 4 is the end view, let's say a top view, of 4 parallel conductors. 4 parallel conductors. Each conductor carries a current of 3 amps out of the page. So it's coming towards you, right? This is why I put it like this. Okay? So it's pointing outward, out of the page. And each of them has a length of 10 meters. Now the distance between these 4 parallel conductors is taken to be 8 centimeters. The question is very simple. Get me the net magnetic force on wire 2. So this is wire 2 here. Okay. What's the net magnetic force on wire 2? So how do you do? Of course, you know that 2 parallel wires that are carrying current in the same direction attract each other. And 2 parallel wires or anti-parallel wires, basically the current are opposite, in opposite direction, they will repel each other. Okay? So let's look at on 2. So on 2, what do I see? Of course, there will be an attractive force from 1. So there is a force that's going in this direction. And this is force on 2 by 1. And I know what is the magnitude of F alpha beta. It's just mu naught, length of the wire, where I'm looking the force which is applying, I alpha, I beta, divided by 2 pi, the distance between alpha and beta. Basically the perpendicular distance. If I have 2 wires carrying 2 currents, I alpha and I beta, and they are separated by a distance of R alpha beta, what's the force between them? The force between them is given by this. So the L is the length of the wires. Okay, so I know what's F21. I know it in magnitude and I know it in direction. Now on 2, what's the other force? Of course, there is an attractive force from 3. So there is also F on 2 by 3. But these 2 forces will be equal and opposite to each other because the current is the same and the distance is the same. The current here is the same. So let's say I1 is equal to I2 is equal to I3 is equal to I4. So this is equal to what? 3 amps. Okay. And also the distances are the same. So you know that basically F21 and F23 will cancel each other. Okay. They are equal in magnitude and equal in opposite in direction. They are equal in magnitude because the currents are the same and also the distances are the same. Okay, finally, the last one will be F on 2 by 4. So it will be also another force, right? Let me erase this. Let me use another pen, another color. Okay, so of course, these 2 are equal and opposite to each other. Okay. F21 plus F23 vectors, this is equal to 0. They are equal and opposite to each other. Let's calculate F net on 2. So F21 plus F23 plus F on 2 by 4. So F net on 2 is just F24. Okay. Now what's F24? It's an attractive force. So F24 will be like this. F24. Okay. Now in magnitude, what is F24? Easy. It's mu naught L. I know L, by the way, is 10 meters. I2, I4 divided by 2 pi, the distance between them, which is 2d. So I know mu naught 4 pi 10 to the power minus 7. L is 10. I1, I2, I4 is basically 3 times 3, so 9, divided by 2 pi. Now the distance here is what? 8 centimeters. So you do 10, so 16 centimeters, so 0.16. And you calculate this, you know everything. So of course it gives you this answer. Okay, is it clear? Great. Now, as we said in class, and I gave you this example in class, now let me put them in a square. So here I have I1 pointing outward. Here I have I2 pointing inward. Here I have I3 pointing outward. And here I have I4 pointing inward. And of course, I give you this distance here. Of course, this distance here, they are the same. Okay? The distance is just 8 centimeters. Okay? And now I ask you to calculate the same question. The net force on wire 2. Okay? Okay. Can you do that? We did it in class already. Once you do that also, I want you to calculate the net magnetic field here at the center of the circle. At the center of the square, okay? Is that clear? So what I want in this problem that I'm giving you now is to calculate net force on 2, okay, in magnitude and direction. Second, calculate B net, which is the net magnetic field at the center of the square. Great. Okay, now let's solve this problem, which is extremely important. Read it very carefully. So we have 2 long straight wires that penetrate normally the plane of the paper at the 2 vertices of an equilateral triangle as shown in the figure. They carry each 3 amp out of the page. So the question is very simple. Find the magnetic field at the 3rd vertex, P. What is the magnetic field in magnitude? Of course, I want it in Tesla as well. Okay, great. Let's solve this problem. So what do you see here? Of course, here these 2 currents are pointing out. Okay, they are coming towards you. Okay. And the current is 3 amp. Now here they will create a magnetic field. Now, how will be that magnetic field? Let's call this wire Y1 and this wire Y2. Now I want to calculate what the magnetic field created at P. So I want to calculate BP, B net at P. Of course, B net at P will be B1 at P plus B2 at P. B1 being the magnetic field created by wire 1 and B2 being the magnetic field created by wire 2 at P. Now let's draw them. Let's draw B1 and B2. So you know that the magnitude will be the same, right? How do I know that the magnitude will be the same? Because the current is the same and the distance is the same. So in magnitude, B1 is equal to B2. In magnitude, let me just put it here. So in magnitude, B1 is equal to B2 and it's equal to 1. To what? Mu naught current I, 1 and 2, because I1 is equal to I2, which is capital I, by the way. Sometimes I call it capital I, sometimes I call it small I, divided by 2 times the distance. So let me call it 2 pi d. D, of course, is equal to 3 centimeters, right? So you can write it here. Of course, this distance here, D, is 3 centimeters. That's the distance between the vertices. It's an equilateral triangle, of course. So D is equal to 3 centimeters, and you have D here, you have D here, you have D here. And this angle is 60 degrees, of course. This angle is 60 degrees. This angle is 60 degrees, which is pi over 3, right? Okay, great. So I know B1 and B2 in magnitude. Okay. So what are they? B1 in B2, I can calculate it. 4 pi 10 to the power minus 7 multiplied by I, which is 3 amp, divided by 2 pi multiplied by D. What is D? Of course, D is 3 centimeters. So you put it in meters, 3 10 to the power minus 2. You simplify, and then how much do you get? You get 2 10 to the power minus 5 Tesla. Okay, and this is B1, which is equal to B2 in magnitude. Now, that's still not the question. The question is to get the net, okay, B net in magnitude. Okay, now let's draw B1 and B2. Of course, let's throw this. When I'm here, if the center is here, you know, at any distance, at any, let's say, point located on my circle of radius D, I have the same magnitude of magnetic field. So now, of course, using the right-hand rule, the current, my thumb is pointing outward in the direction of the current. Of course, my fingers will be pointing in this direction. Oops. So B1 will be like this. Do you agree with me? Right-hand rule. Great. Okay, good. Now, what do you think here? Of course, this is 90 degrees. Okay? This angle here will be 90 degrees. So what do you think? What should be this angle here? Because this angle here is 30 degrees. Do you agree with me? I hope you see what I mean. Okay, so this is B1. Because this, I will take this as my x-axis and this as my y-axis. So B1 has two components, B1x and B1y. What is B1x? B1x is negative, right? So it's minus B1, magnitude of B1 cosine, what? 30 degrees. I hope everybody sees why this is 30 degrees. Okay. Do you see why it's 30 degrees or not? You can look at it this way. This is going straight, right? So this is 60 degrees, you agree? 60 degrees, I add 90 degrees to it. So 60 degrees plus 90 degrees is equal to what? 150 degrees. That means this is 30 degrees. Okay? There are many ways to see it, but this angle is 30 degrees, of course. And by2 is positive, okay? It's just plus b1 sine 30 degrees. Now let me do the same for b2. b2, let me take another color. Let me take a green color, for instance. So b2 is created by this one, 2. Okay? So right-hand rule, you see, the current, my thumb is in the direction of the current. Of course, my fingers will be pointing in this direction. And it's tangent. Okay? And it's tangent to the circle. You see the circle, the red circle? It's tangent to the circle. And it has the same magnitude. Okay, so it's up here, of course. Okay? And this is B2. B2 has the same magnitude as B1. Okay? So you see that the net, of course, will be along the x direction, the negative x direction. This is B net. Okay? So B net is along the negative x. So B2, okay, B2 is here. Again, what is this angle here? 30 degrees. So B2 has two components, along x and along y. Along x, what's the component? Is B2x and B2y. What is B2x? B2x is minus B2 cosine 30 degrees. Now, what is B2y? B2y is minus also B2 sine 30 degrees. Now, B net, you see, if I add them, of course, it will be B1x plus B2x, B1y plus B2y, And you see that, of course, B net will give you -2 times B1 cosine 30 degree, and along Y, 0. See, they are opposite to each other. Of course, I knew that. I see here, this part and this part are opposite to each other. Of course, 0. So my B net is purely along X, so I know the direction. B net is along X, and I know the magnitude. So B net is just 2 times B1, which is 2 10 to the power -5, times cosine 30 degree. Cosine 30 degree is square root of 3 divided by 2. And you calculate this, of course, it gives you 3.46 10 to the power -5 Tesla, which is 3.5 10 to the power -5 Tesla. Is it clear? Just vectors, as in physics 101. Okay. So you are just careful, you know the angles. Okay. Is it clear? Great. Muhammad, is this clear? Abdullah Al-Ghamdi, is this clear? Great, mashallah. If I give you this in the final exam, full mark. Great. Now, let me go now to a more interesting problem. Same idea, but a little bit more difficult. Okay, let me erase everything here. Okay, solution is given here, and you see. Okay, let me just do this. Okay, now instead of giving you this problem, which is an equilateral problem, well, I will give you this one. I have basically here I pointing towards you, let me call it I1 is equal to 3 amp, and here I2 pointing towards you, 3 amp. I can change the currents, okay? I can put a different current, okay? But here, let me keep it the same current. But they are separated by a distance here of 5 centimeters. Now, I'm asking you to calculate what the net magnetic field at the point P here. Now, where is located P? P is located here. So here you have 90 degrees, here you have 3 centimeters, and here you have 4 centimeters. So basically, I have a right triangle, a triangle which is a rectangle. Okay, 3 centimeters, 4 centimeters, 5 centimeters, hypotenuse 5 centimeters. Now I'm asking you to calculate the net magnetic field here. Okay, and I want it in unit vector notation and in magnitude direction notation, magnitude angle notation. Okay, it's a little bit more difficult than the previous one, but the idea is the same. Yeah, you just find the angles. So that's my question to you. Now, if you want to go further, you can change the magnitude of the force of the current. But here I keep the magnitude of the current the same. Next question. Equilateral triangle again. It's easy. Okay. Here I have 60 degrees, of course. Here I have 60 degrees, of course. Here I have 60 degrees. Let's read the question. 3 long parallel wires pass through vertices of an equilateral triangle with side length 10 centimeters, as shown in the figure. Each wire carries a current of 15 amp. So I know I, 15 amps, and I know D, 0.1 meters. Find the magnitude of the force per unit length on the upper wire. This is the upper wire here. Great. So what do you think? So this is the upper wire. Let me call this wire 1, 2, and 3. Okay. So I want to get net force on 3. Okay. So what is net force on 3? Net force on 3, of course, will be net force will be force on 3 by 1 plus force on 3 by 2. Now, how is force on 3 by 1? So you see, wire 3 and wire 1 are anti-parallel currents. They are parallel in direction, but one is pointing out, one is pointing in. So what do you think? It will be a repulsion, of course. Okay. So F on 3 by 1 is just going in this direction. This is F31. Okay. 1 and 3 are repelling each other. Now you see 2 and 3 are attracting each other. So F on 3 by 2 is pointing in this direction. F on 3 by 2. Okay. Great. So here the currents I1 is equal to I2 is equal to I3 is equal to I is equal to 15 amp. So let me just calculate this. Of course, F31 has two components. What are the components? You see here? Because this angle here comes back here 60 degrees. So it will be F31 cosine 60 degrees, F31 sine 60 degrees. Okay. And F32, same thing. But of course, here I will have plus F32 cosine 60 degrees. And here I have minus, okay, because this is 60 degrees. I'm in this quadrant here. So I will have minus F32 sine 60 degrees. Don't forget that F31 is just mu1, mu naught L. Okay. So let me divide by L. Okay. Let me divide F. So I have mu naught L. I will come back to this. I1, I3 divided by the distance between them, which is 2 pi. The distance between them is 0.1. So it's mu naught L current square divided by 2 pi times 0.1. This in magnitude is equal to F, of course, 32. Okay, because the current is the same and the distance is the same. So in magnitude, they are the same. So let me write that down here. F31 in magnitude is equal to F32 in magnitude. Okay. So my F net, you can see that this length here is the same as this length here. So my F net will be effectively along X, okay, in the X direction. F net is here. And I know it. I will have just 2 times F31 cosine 60 degrees, which is this plus this. Along Y, I have this plus this, which is just 0. Okay, so this is just equal to 0 along the Y direction. Here I will have just 2 mu naught L current square divided by 2 pi times 0.1. And then don't forget the cosine 60, of course, okay? So let me divide by 2. So my F net divided by L, sorry, is 0 along Y, and along X is just 2 times mu naught current square divided by 2 pi times 0.1 cosine 60 degrees. That's it. So I know everything. I know mu naught, I know I square, I know cosine 60 degrees, I know the distance, I can calculate everything. And of course, you will find that it's equal to what? 4.5 10 to the power minus 4 Newton per meter, okay? Because it's a force per unit length. Okay, great. Now let's go to the next question here. Is it clear? Okay, just vectors. You remember vectors in physics 101? Now that's what we carry here. But of course, now we have new formulas for, you know, magnetic force and etc. etc. So I have a cylindrical cable of radius 15 millimeters. It carries this current uniformly distributed over its cross-sectional area. We already solved this type of question. At what distance from the center of the wire is there a point within the wire? At what distance from the center of the wire is there a point within the wire where the magnitude is 100 microtesla? So you know that B1, which is B inside, when R is smaller than capital R, this is just mu naught current I divided by 2 pi R square multiplied by the distance R. Okay, great. So here I gave you B1. B1 is 100 micro Tesla, 10 to the power minus 6 Tesla. So basically it's 10 to the power minus 4 Tesla. And the question is, find me R. Well, R will be B, which is 10 to the power minus 4 Tesla, divided by what? Divided by mu naught I divided by 2 pi radius square. So I know everything here. Okay. I know B, I know mu naught, I know I, and I know radius square. You do it, you will get 4.5 10 to the power minus 3, okay? Which is nothing but 4.5 millimeters. Very simple. Okay, we already solved it. Now let's go to the next problem, which is also straightforward. I can skip it. We have two infinitely long straight wires that cross each other perpendicularly, as shown in figure 6. The wires do not touch. What's the magnetic field at point P? Of course, if I call this wire Y1, this core wire I call it Y2. So net magnetic field at P is B1 at P plus B2 at P. Now tell me about B1. What's the direction of B1? Right hand rule, my thumb along the direction of the current. Of course, my fingers will be pointing inward. So B1 is directed inside the page, inward, inside the page. What about B2? B2 thumb across the, along the current, my thumb will be pointing outward. Okay, so B2 is directed outside the page. This guy is directed outside the page. Now, as I told you, inside the page, I give it a negative, okay, because it's minus, and outside I give it positive. So now let me project along Z direction. Z direction, so negative is minus Z, of course. Positive is plus Z. It's along the direction of K hat. This is along the direction of minus K hat. So let me project along the Z direction. Outside is positive. So my B net, so in will be minus B1 plus B2. Okay. Minus here because it's pointing inside, plus because it's pointing outside. Now what is B1? B1 is just mu naught I1 divided by 2 pi distance. So that's the distance is 30 centimeters, basically 0.3. And B2, I know it, mu naught I2 divided by 2 pi distance, 40 centimeters, so 0.4. So let me calculate now. B net is just equal to, let me take as a common factor, mu naught divided by 2 pi. So I'll have what? Mu naught divided by 2 pi. Okay. So here I will have what? I will have I1 divided by 0.3. And of course, don't forget the negative sign. And here we'll have I2 divided by 0.4. Don't forget the negative sign. Of course, mu naught divided by 2 pi, this gives you 2 10 to the power minus 7. Do you agree with me? So I1 is equal to 3 amp minus 3 amp divided by 0.3 plus I2 is equal to 5 amp divided by 0.4. And you calculate this, how much do you find? you find 5 10 to the power minus 7, which is just 0.5 microtesla. And it's positive, that means it's pointing outside the page. Okay, so 0.5 microtesla, and of course it's out of the page. Okay, let's solve this problem here, which is a very good problem, but let's go very quickly. A long solenoid has 150 turns per centimeters. Okay, so here I'm giving you n with 150 per centimeter. Of course, I put it in meters, so it gives me 150. 1 centimeter is 10 to the power minus 2 meters. So the number of turns is just 1500 turns per meter. And I give you the current I, 0.15 amp. An electron moves in the solenoid. Okay, of course, the electron will feel the magnetic field created by the solenoid. An electron will be moving at constant speed within the solenoid in a circle of radius 2.7 centimeters perpendicular to the solenoid axis. Okay, this makes sense. Okay, because the solenoid, the electron is a charged particle moving inside a magnetic field. Of course, now the magnetic field and the velocity will be perpendicular to each other. So it will be moving in a circle. If they were not perpendicular to each other, the electron will be moving in a helical path, okay, in a helix. Here they are perpendicular to each other. I did not tell it to you, but I said it here. Constant speed, perpendicular to the axis of solenoid. You know that the magnetic field will be in the axis of solenoid. The velocity will be perpendicular to it. So my electron has a constant speed and a uniform circular motion. Okay? So you know that the magnetic force, very simple, what the magnetic force magnitude for my electron is QV cross V. Now in magnitude, let me take it in magnitude, will be the charge of the electron, E. I take absolute value, of course. V, B. Sine the angle between them. They are perpendicular to each other. So sine 90 is equal to 1. This magnetic force is just equal to what? It's a centripetal force because I'm going in a uniform circular motion. So this is mv square over r. R being the radius of the circle. Okay? So if I solve these two equations, what do I find? I find that V is equal to, so you simplify here, of course. So it's E, B, R, of course, divided by M. But what is this B? This B is a B created by a solenoid. B is just mu naught N I. Okay. So V will be E mu naught N I. N is the number of, and is this basically. Okay, divided by the mass of the electron. So I know everything here. I know E, 1.6 10 to the power minus 19. I know mu naught, 4 pi 10 to the power minus 7. I know N, 15 10 to the power 3. I know I, 0.15. And I know the mass of the electron. What's the mass of the electron? Formula sheet, 1.31 10 to the power 31. Sorry, 1.11. Okay. 10 to the power minus 31. And you calculate and you find the velocity of your electron. Okay. So here I'm combining two chapters. Okay. And you know how to do that. The first thing is to get B, which is the B from my solenoid. Now, once I get B, the problem is just a chapter 28 problem. Okay. Magnetic force on a charged particle. QVB, of course, here B is perpendicular to B. So you have a uniform circular motion, and we already demonstrated that, you know, the radius is QB. No, sorry, it's MV divided by QB, right? This was the radius, right? Yes, MV divided by QB. You use that, and then you get what you want. Okay, let's go to the last problem here, which is extremely important. Okay. So read the problem carefully, and then we solve it. First, let me just remind you that if I have two wires conducting current parallel to each other, FAB is just mu naught L, the length of the wire, IAIB divided by 2 pi, the distance RAB. It's in your formula sheet, okay? So let's read the problem. We have 3 long parallel wires, 1, 2, 3, carrying current 2, 10, and 5, respectively. So here's the current is going in this direction. Here's the current is going in this direction, 20 amp, 10 amp. Here's the current is going in this direction. Of course, this is I1, this is I2, and this is I3. So part of wire 2 and 3 are fixed to a hard insulating. So here, this is very important. It's insulating. So it's just fixed to it. So it actually the force is between the wires, okay? Because this rectangular frame is just, insulating. And I give you the dimensions. Now the question is net force on the rectangular loop, which is insulating, by the way, but I attach it to wires that are attracting each other or repelling each other. So the question is, what's the net force on the rectangular loop due to the fact that it's attached to wires? Okay, great. Let's calculate that. So I know that this is 10 centimeters. Okay. This is 10 centimeters. So in reality, I just need to get what the net force on these two part of my wire. Okay, great. So I can consider them very long. And then I apply the formula. Okay, great. Now, the net force on my rectangular loop. So first, what's the force applied on this side of my rectangular loop? Force here, I will have what? Force on 2 by 1. Do you agree with me? Yes, it's an attractive force. It will attract it. What about free? It will repel it. So the force here, F on 2 by 3, is a repulsive force, okay? Both of them are pointing upward. Now, what about this side here? What are the force applied to this side? First, I will have what? Force on 3 by 1. What do you think? Will it be an attractive or an repulsive force? It will be a repulsive force, right? Because they are going in opposite direction. So here I will have force on 3 by 1. Now, what about 2? I will also have repulsive force, which is pointing downward. I did not draw them in scale, by the way, okay? So this is not the scale. I'm just giving you the directions. So this will be force on 3 by 2. Okay? Great. I'm just drawing the direction here. So my net force on my rectangular wire, here, of course, nothing happens because it's insulating. So nothing has here, nothing happens here. So my net force will be what? F21 plus F23 plus F31. Okay, so basically this one plus this one plus this one plus this one plus F32. Okay, do you agree with me? Okay, do you agree with the directions? Good. Now, F23 and F32 are equal and opposite to each other. Do you agree? This is 0. Why? The Alford low pair. Okay? Let me write it down. F23 is equal in vectors to minus F32. So they cancel each other. So my net force is very simple. It's just F21 plus F31. So F21 and F31, so these two cancel, this one and this one cancel. So now these two forces are the forces that act on my rectangular wire. Okay, let's calculate them now. Let me project along the z-axis. Let's say this is my z-axis. or my y-axis if you want. Let me call it y-axis. So if I project along the y-axis, so my f net, so I will have plus f21 minus f31. Now what is f21? Well, it's mu naught L divided by 2 pi. Now here I will have I1, I2, and the distance 2 pi. What the distance between them? Of course, the distance between 1 and 2 is this distance, 3 centimeters. So 0.03. Okay. And then here I will have minus mu naught L. By the way, what I call L here is 10 centimeters. Okay, so L is equal to 0.1 meters. L is the length here, 10 centimeters. Now it's I1, I3 divided by 2 pi. The distance between these two gentlemen is 5 centimeters, right? No, I'm looking at between 1 and 3, right? So be careful. I'm looking at the distance between 1 and 3, which is this. So 8 centimeters, okay? 5 centimeters plus 3 centimeters, so 8 centimeters. So 0.08. So I know everything here. I know mu naught, I know L, I know I1, I know I2, I know I1, I know I3, I know the distances. So I calculate, and you will get, of course, 1.1 10 to the power minus 4. And it will be positive, okay, because this is larger than this. And it will be positive, so it will be pointing towards Y1. Okay. Is that clear? Okay, great. Let's stop here. Please solve all the rest of the problems. Okay, you solve the same idea coming again and again and again. You have to solve as much problem as possible. Okay, and you understand. Of course, understanding is the basic, but that's not enough. You have to solve problems. Okay, solve problems. Solve my recitation problems. Okay, they are the best recitation problem you can find out there. No, I'm joking, of course, mashallah, but they are not bad. So solve them and solve any other resources you find useful. Okay. Thank you very much. Assalamu alaikum.